Have you ever stopped to think about how we power, well, everything? Nearly all the electricity we use comes from a single, incredible principle. And it's not some crazy, complicated machine. Nope, it's a kind of beautiful magic that happens with just a magnet and a bit of movement. Today, we're pulling back the curtain on that secret: electromagnetic induction.
So here's the big question, right? It almost sounds like a trick. How can a plain old magnet, no batteries, no plug, just conjure up electricity from basically nothing? That's the mystery we're going to unravel together.
So where does this story even begin? Well, it starts where a lot of stories about electricity do, with a brilliant, super curious scientist named Michael Faraday.
Okay, picture this. It's 1831. People already knew that running electricity through a wire creates a magnetic field. But Faraday, he had this nagging question. Could it work the other way around? Could a magnet, all by itself, create electricity? The experiment he cooked up to find out was just, well, it was beautiful, so simple.
So check this out. Faraday grabs a coil of wire, hooks it up to a meter that detects current. Then he takes a regular bar magnet and he just moves it. The second he pushes that magnet into the coil, the needle on the meter jumps. A current, out of nowhere. But then he stops the magnet and the current's gone. Pull the magnet out, the needle jumps again, just in the other direction. And that was it. That was the secret. It wasn't the magnet itself, it was the motion.
And with that one simple observation, he had discovered a fundamental law of the universe. He gave it a name: electromagnetic induction. It's the whole process of generating voltage not with batteries, but just by changing the magnetic environment around a wire. It wasn't magic after all, it was physics. Now, a discovery this profound, this world-changing, couldn't just be an observation. It had to be described by laws, the official rules that explain how our universe is bolted together. So to really get these laws, we got to talk about something called magnetic flux. Here's a way to think about it. Imagine the magnetic field is like invisible rain falling from the magnet, and your coil of wire, that's like the opening of a bucket. Magnetic flux is just a fancy way of saying how much of that invisible rain is passing through the opening of your bucket right now.
And that brings us to the first big rule, Faraday's law. This one answers the question, okay, how much electricity do I actually get? And the answer is surprisingly simple. The voltage you create is tied directly to how fast that magnetic flux is changing. You want more voltage? Move the magnet faster. Use a stronger magnet. Add more loops to your wire. Anything that makes that rain change more quickly gives you more power. Simple as that.
But which way does the current flow? That's where Lenz's law comes in. And honestly, you can just think of it as nature's law of being difficult. The current you make will always flow in a way that creates its own magnetic field to fight back against what you're doing. So if you push a north pole in, the coil instantly generates its own north pole to push you away. It's nature's way of saying, hey, you don't get energy for free. You gotta work for it.
So let's just put it all together here. You've got two sides of the very same coin. Faraday's law tells you the magnitude, how much power you're making. And Lenz's law tells you the direction, which way that current's gonna flow. You really need both to get the full picture. But this whole story gets even more interesting, because induction isn't just about a magnet and a totally separate wire. This effect is so powerful, it can happen inside a circuit all by itself. Kind of like an echo of the current bouncing back. And this leads us to two new related ideas. First, you've got self-induction. That's when a changing current in a wire creates a magnetic field that actually pushes back on itself, resisting the change. It's like the circuit has its own inertia. Then you've got mutual induction. This is when one circuit's changing magnetic field is so strong, it actually creates a current in a totally separate circuit that's just sitting nearby. No wires connected, just influence. And the property that measures all of this sort of electrical inertia, has a name. It's called inductance. The higher a circuit's inductance, the more it's going to fight back against any change in current, and the stronger these induction echoes are going to be. Okay, so we've got the theory, we've got the laws. But why should you care? Because this one single principle is quietly humming away in so many things you use every single day. Let's start with an absolute classic,
That raw, amazing sound of an electric guitar, that is pure 100% induction in action.
So how does that even work? Well, right under each string, there's a little magnet wrapped in a coil of wire. That's the pickup. When you pluck the string, it wiggles back and forth, and that makes the magnetic field around it wiggle too. That constantly changes the magnetic flux going through the coil, and bam! It induces a tiny electric current that's a perfect copy of the string's vibration. Crank that up through an amp, and you've got rock and roll.
Okay, next up, an application that could literally save your life. You have one of these in your breaker box. It's a safety switch. In Italy, they have a great name for it, the salvavita, the lifesaver. And it's just a little work of genius based on induction.
Here's how clever this is. It uses mutual induction to constantly compare the current going out to an appliance with the current coming back. They should be perfectly equal. But if some of that current is leaking out, say through a person who accidentally touched a bad wire, it creates an imbalance. That imbalance causes a sudden change in magnetic flux, which instantly induces a current that trips the switch, cutting the power in a fraction of a second. Absolutely brilliant.
All right, so from your guitar to your wall, now let's scale it up. Way, way up. Let's talk about what happens when you use induction on a massive scale with magnetic levitation, or maglev, trains.
This is basically induction on beast mode. As these incredibly powerful magnets on the bottom of the train fly past coils built into the track, they induce massive currents in those coils. And thanks to Lenz's law, those new currents create their own powerful magnetic fields that repel the train's magnets, pushing the entire thing right up into the air. It's literally floating on a magnetic cushion that it creates as it moves.
All of these examples, the guitar, the switch, the train, they all bring us to our final and maybe most mind-bending point. We've been talking about magnets and current, but what are we really moving around here? The answer is energy. And this is the deepest secret of all. A magnetic field isn't empty space. It's not nothing. It's a reservoir. It's a place where potential energy is stored. So induction, when you get right down to it, is just the act of tapping into that invisible field energy and converting it into the moving energy of electrons, which we call an electric current. So just let that sink in for a second. The energy isn't really in the wire or in the magnet. It's stored invisibly in the field that connects them both. Faraday didn't just give us generators. He gave us a totally new way of seeing the space all around us. And that leaves us with one last question to chew on. If something as vital as electricity can be unlocked just by waving a magnet through an invisible energy field, what other unseen forces, what other untapped potentials are all around us, just waiting for us to find the key? What else is shaping our reality right now, just beyond what our eyes can see?